title of this week's quiz is AC Thevenin, but actually the later questions in the quiz are more concerned with Kirchhoff's laws and how to apply them to AC circuits when we use phasors to analyze them. So I wanted to add a short video where I just run through one or two examples of those later questions, showing you how to do the Kirchhoff's laws calculations in Octave. So I'm going to begin here. I'm on question 6 of the preview quiz, and you can see that this question concerns Kirchhoff's voltage law in this circuit here. So I'm going to redraw the circuit on paper here. I've got a voltage source and an inductor and a resistor. And the key thing in the circuit here is that the phasor voltage is labeled on each of these elements, and the orientation of each phasor voltage is also shown, and that's going to be important when we do the calculation. So this voltage here, I'm going to call it Vs. I'll fill in the actual value specified in the question in a minute, but this is the variable name that I'm going to use. We have the inductor phasor voltage, which I'll call VL, and the resistor voltage, which I'll call VOR. So the idea with Kirchhoff's voltage law is simple enough. As you move around any closed path in the network, arriving back to the point where you started, the net increase and decrease in voltage as you go through each branch in the network must all add up to 0. So you arrive back at the same voltage that you began at. Now, to make things clearer here, I'm just going to label my nodes. I'm going to call this one node 0. Call this one here node 1, and I'll call this node 2. So the sequence that we're moving around this very simple circuit is beginning at N0, we're going to go to N1, and then we're going to go to N2, and then we're going to go back to N0. So we move in one continuous path clockwise around the circuit, arriving back at the node where we began. So each time we move from one node to another, we step up or step down in voltage, and the voltages here are all represented as phasors, but we just add up those phasors as we move around, and when we get back to the point where we started, we should have arrived back at the same voltage. Now when we add the voltages, the phasors together, it's important that we take into account the direction of these arrows here. So if I pass through a branch in the same direction as the arrow, then I'm going to add that voltage. But if I pass through a branch in the opposite direction to the voltage phasor, then I'm going to subtract that phasor. So the direction of the arrow is significant here. So in this case, beginning at node 0, the first movement from one node to the next, we go up Vs, so that's plus Vs. And then going from N1 to N2, we go backwards through VL, so I'm going to subtract that, so minus VL, because we're going in the opposite direction to the arrow. And then moving from N2 to N0, we go through the resistance, and again we're going the opposite direction to the phasor arrow, so that's minus VOR. And Kirchhoff's voltage law tells us that the three of those phasors have to add together to give us 0. And now if I rearrange this equation, because it's VOR that we're interested in, I'll be able to isolate VOR on its own on one side. So VOR is equal to Vs, the supply voltage, minus VL, the inductor voltage. And remember that these are all complex numbers which represent phasors, so the magnitude of each of these is the magnitude of the sinusoidal oscillation, and then the angle of the complex number represents the phase of the sinusoidal voltage. So this is what we're going to actually calculate in Octave for this particular circuit. So I'll just jump back to Octave here. Now you could write this out in an M file, but I mean this is such a simple question that I think it'll be just more appropriate to type it in real time in the command window. However, I'm going to use variables to store each of these phasors in. I just find it a bit easier to enter them one at a time. So I'll put in Vs first, and that's going to be 30. And in fact, the phase angle of that phasor is 0. So I don't need to worry about adding an angle there. I'll just enter it as 30. I'm putting a semicolon to stop it from just printing out each time it assigns a value to a variable, to stop it printing it out on the screen here. That's all the semicolon does. Put in VL. VL is equal to 2.9988. but this time I have to add a phase angle to the complex number. So I'm going to multiply that by exp 1.42j. So what I'm doing here is this is the exponential function, meaning it's going to raise the mathematical constant e to the power of whatever is inside the brackets here. Now the important thing about e, or the thing that makes e significant here, is that when you raise it to the power of a complex number, or sorry, of an imaginary number rather, you will always end up with a complex number of magnitude 1, but with an angle exactly equal to the magnitude of the imaginary number. So in this case, an angle of 1.42 radians. So this gives us a phasor which has got the right angle, but only got a magnitude of 1, and then we multiply it by the magnitude that we want in order to scale it up to the size that we need. So that's VL. Now finally, we're able to apply my formula, which is VR is equal to VS minus VL. So that was what I worked out on paper. And the result for VR is this number here, shown in Cartesian form, so a real and imaginary part. Now the 4 possible answers that are shown in the question are in polar form. In order to see the magnitude and phase of VR, I can use the absolute value function to get the magnitude. So that's 29.698 volts. And to get the angle, we use the angle function. So again, angle VR, and it is very close to minus 0.1. So looking at our possible options here, you can see that option A is almost a perfect match for the number that we've calculated there. So with a phase angle of minus 0.1 radians, so that's very, very close to minus 0.1, and 29.698, very close to 29.7. So A is our correct answer in this question here. Okay, so after I've completed that question, I'm just going to clear to get rid of all of the variables out of Octave's memory. And I will also just clear command window here, just to tidy up visually on the screen what we're looking at. I'm going to move on to the next question here. So this one is question 7. Now this is an example of Kirchhoff's current law. So for this circuit here, we've got a voltage source, a resistor, capacitor and inductor, and we're interested in the currents at this node here. So let's just draw this one out on paper. So I have voltage source, resistor, capacitor and inductor. So in the question, these are specified as C3, L2. But the most important thing here, the thing that's significant for answering this, is that 3 currents are shown, 2 entering this node and 2 leaving the node. So these are shown as I1, I2 and I3. So this one is I1, this one is I2, and this one is I3. So what Kirchhoff's current law tells us is that the sum of the currents entering any node has to be 0. So another way of putting that is that whatever currents are arriving at the node, whatever they add up to, the current entering the node has to be the same as the total amount of current leaving the node. You can't have any electrical charge accumulating at a node. So the total amount of current coming into it has to be constantly in balance with the total amount of current leaving it. So for our node here, we can say that I1 must be equal to I2 plus I3, because I1 enters the node and I2 and I3 are leaving the node. So the total entering must be equal to the total amount leaving. Now in the question, what we're asked to calculate is I1. So that formula is going to be enough for us to get the correct answer here, just once we can add up these 2 phasors here. So that's what I'm going to do in Octave. Say I2 is equal to 171.39, and this is milliamps, so I'm going to raise that to, or multiply it by 10 to the power of minus 3. And then I also need to apply a phase angle there of 2.08 radians. So that is I2. I3 is equal to 62.356. Again, that's milliamps, so E minus 3 for times 10 to the minus 3. And the phase angle in this case is minus 1.06 radians. So that's I2 and I3. So finally, to calculate I1, it's just the sum of I2 and I3. Now, it's shown here in Cartesian form, but the answers in the quiz question are in polar form. So I'm going to get the absolute value of I1 and the angle of I1. So you can see there it's 109 milliamps and 2.07 radian phase angle. So let's see if this is a good match for any of these. Yeah, D here is very, very close to that. So D is the correct answer for this question. Okay, let's take a look at one more. So again, I'll clear the memory in Octave and clear my command window. So this one is Kirchhoff's voltage law again, very similar to the first example that I did. In this case, we're trying to calculate V. So let's just take a look at it on paper first. What have I got here? Voltage source, capacitor and resistor. I have Vs, my supply voltage, Vc and Vr. So this is my circuit. Values are specified for each of these, but what we're interested in is what is the relationship between V and these other two phasors which are given. So V is what we're trying to calculate. I'm calling V Vs in my diagram here just since I've got three voltages labeled. So what Kirchhoff's law tells us, again I'll label these nodes N0, N1, N2, and as we go around the loop beginning at N0, moving to N1, moving on to N2, and finally back to N0. So a complete closed loop path around the circuit. Each time we move from one node to another, we step up or step down by the voltage in that across that element. So going from N0 to N1, we go up through the voltage source and we're moving in the same direction of the arrow of the phasor. So in that case, it's going to be plus Vs. And then we move on from N1 to N2 through the capacitor. Now we're going in the opposite direction to the arrow of the phasor Vc. So that means we're going to subtract Vc. And when we move from N2 down to N0, again, we're going counter to the direction of the arrow of Vr. So it's going to be minus Vr. And these three all have to add up to 0. So we have to wind up at the same voltage that we ended up, or that we began at. So rearranging this, we're trying to get Vs in this case. So rearranging this equation, Vs is equal to Vc plus Vr. So this is the formula that I'm going to use to calculate Vs. So Vc is equal to 22.281 with a phase angle of 1.52 radians. Vr is equal to 11.5 with a phase angle of 3.1 radians. And V finally is the sum of those two, so Vc plus Vr. And putting that into polar form, I get the magnitude and the angle of V. So 24.98 volts with an angle of very close to 2 radians. So that looks like answer B in this case. So that's the third example. Hopefully that gives you some idea how to go about these Kirchhoff's laws questions. Once you're able to enter the phasor values in this notation in Octave or in MATLAB, it becomes very easy to manipulate these numbers and to do this arithmetic. But if you're doing it on your calculator, which can be a useful skill for exams and so on, it's definitely more unwieldy dealing with these complex numbers. Whereas the power of Octave and MATLAB is that once you're able to enter the values in an efficient way in polar form, it becomes very, very straightforward to do these kind of phasor calculations. So I'll leave it there.